Marimar is made easy, no more fear. Target online class, we got you. Wherever you want to from, we got what you need. Target online class.
Good day, viewers all over the world. You are welcome to Toydel online class. Today we want to talk about probability. So today we are actually introducing probability. So what is probability? What is probability? As we have it on the board. Probability is a measure of likelihood that a particular event will occur in any one trial or experiment or carried out in a prescribed condition. So probability is the likelihood, from the word likelihood. Probability is the likelihood that a particular event will occur in any one trial or experiment carried out in a prescribed condition. We can also say that probability can be defined as the likelihood of an event happening. That is, probability can be defined as the likelihood of an event happening. We can also define probability that way. Thus, if an event cannot happen, we are 100% sure that an event cannot happen, the probability is 0. If we are certain that an event will never take place, the probability is 0. For instance, for us to be able to have, I'm talking about ideal situation. I'm not talking about all this scientific method. For us to be able to have a goat or a dog that will give birth to a human being in the normal scenario, I'm not talking about all this scientific approach, is 0. Or for us to be able to get human being that has 4 heads, is 0. The probability is 0 because it does not make sense. It can never happen in an ideal situation. So if we are sure that an event can never take place, the probability is 0. If you are certain that an event cannot take place, the probability is 0. And if an event is certain to happen, the probability is 1. If you are sure that an event will surely take place, the probability is 1. For instance, the probability that every creature made by God will die. Of course, we don't know the time, We cannot say that today or tomorrow or in the next 100 years. But the probability that every living thing will die is 1. We are certain that every living thing will surely die. So the probability is 1. So now the probability of an event happening or not happening lies between 0 and 1. That is, the probability that an event will happen, let's say probability, let's say call the event X, and that event will not happen is 1. Or we can write that way, will say 0 less than or equal to probability of X, then probability of 1. So this is the range of probability. So when we talk about probability, is between 0 and 1. The probability that an event will happen, the event will not happen is 0. The probability that an event, we are sure that an event will happen is 1. Then every other probability is between 0 and 1. So I'm trying to establish this fact so that we are going to be sure when we are dealing with problems under probability. We should be sure, because under probability you cannot get negative answer. It's not possible. Then you can never get answer that is more than 1, because the probability that an event will happen is 1. So you can't say you work question under you are solving problem under probability and say your answer is 2.5. It does not make sense. Under probability, the range of whatever answer you are going to get should be between 0 and 1. So that simply means that the solution under probability lies between 0 and 1, and it cannot be negative, because when I work when I solve the problem under probability, I got minus 1 over 2. So this is the range that we can actually come across under probability. So we quickly talk about types of probability. We have experimental probability. That's empirical. Experimental probability. I'm going to talk about 2 here. We are going to talk about empirical. That is experimental probability. Then we also talk about the second one, which is classical or theoretical probability. These are the 2 types that we are going to talk about. Under experimental or empirical probability is based on previous known results. So under experimental or empirical probability, that is actually based on previous known results. For instance, if you toss a coin, we know that it's either head or tail. If you are dealing with a die, you know, a die has 6 faces. So that can be an example under empirical or experimental probability. Then under classical probability, this one is based on the consideration of theoretical numbers and number of ways in which it is possible for an event to take place. So this classical or theoretical probability is actually based on the theoretical number of ways in which it is possible for an event to occur. So under classical probability, of course, when I can be using the 2 words interchangeably. So when I say empirical or experimental, if I say classical, I'm actually talking about theoretical probability. So under that, now under classical probability of an event, let's say the event is A occurring. So under classical probability of an event occurring, the probability of A that an event will occur simply means the number of favorable outcome. The number of favorable outcome all over the total number. This will not be the total number of possible. The total number of possible outcome. So this is the formula that we use under classical or theoretical probability. That's what we are going to have. So remark. Let's briefly take this remark before we continue. Remark. That is, remark simply means what we should take cognizance of. Remark. Total number of possible outcome can be classified. The total number of this possible outcome under classical probability can be classified into equiprobable events and non-equiprobable events. So the total number of possible outcomes can actually be classified into equiprobable, and non-equiprobable events. So we should take note that under the total number of possible outcomes, this the one denominator here under probability of classical or theoretical probability. This total number of possible outcomes can either be equiprobable event or non-equiprobable event. So if we talk about equiprobable events, what do we mean by equiprobable events? We are trying to establish some theoretical knowledge about probability before we actually go into examples. So we must understand all this. So what do we mean by equiprobable events? Events with items having equal number of elements. When we talk about equiprobable events, these are events with items having equal number of elements. For example, when we have a well shuffled pack of cards, So in a pack of cards, people that play cards, what? I think there are 52 cards there. Okay? So whatever you want to do cannot exceed 52. Another example is when we have a fair coin. A fair coin. In a coin, is that it is head or tail? Is that it is head or tail? Or when we have an unbiased dice. When we have an unbiased dice. So in a die, there are 6 faces. 1, 2, 3, 4, 5, 6. So these are examples under equiprobable events. So when we are talking about probability, theoretical probability, which is given by formula, number of favorable outcome all over total number of possible outcome. If the total number of possible outcome actually falls under equiprobable events, then we know that they have specific, we know that the item have equal number of elements. So the probability that it is head is will be 1 over 2. The probability that it is tail, the same thing. The probability that if you toss a die, if you are dealing with unbiased die, the probability that if you toss it, one will come up will be 1 over 6. They have equal outcome. That is what we are trying to say. Then under the second event, under the total number of possible outcome, where we have the second event is non-equiprobable events. Under this second event now, we have events with items having different number. That is, under this, they have the same number at the denominator, the same number of possible outcome, total number of, you understand? Yeah. But under non-equiprobable events, then they can actually have, these are events having different number. For instance, if you consider a class of students, the total number of students in the class differs. In some class, we can have the total number of students can be 20. In some, it can be 100. In some, it can be 35. So we are not sure of the total outcome. So the total outcome here varies, but the total outcome here is actually constant because we are actually considering something that has the same total number of events. Then we quickly define some terms under probability before we take examples. We quickly define some terms under probability. We can just say this is definition of terms. The first one we are going to define is called the sample space. So we discuss the sample. Let's discuss the sample space. Sample space. So what do we understand by sample space in probability? Sample space. If we have a set, say S, if we have a set S that consists of all possible outcomes, this set S consists of all possible outcomes of a random experiment. So a set S that consists of all possible outcomes of a random experiment is called a sample space. And each outcome is called a sample point. A set that consists of all possible outcomes is called a sample space, and each outcome is called a sample point. That's just the definition of that sample space. Then the second one, we are talking about outcome. Outcome. These are some of the terms that we use in probability. Then if you are talking about outcome, what do we actually mean by that? So outcome in a trial, each separate possible result is called an outcome. That is, if you are trying to consider a particular trial or particular example under consideration, each separate possible result is called an outcome. Then we can also talk about events. We can actually talk about events. That's another term that we want to define. An event is a subset. An event is a subset A of a sample space. That is, in a sample space, if you say A is an event, so A is actually a subset of a sample space because we define a sample space a set S that contains all possible outcomes. So sample space contains all possible outcomes under consideration, but an event is actually a subset of this sample space. That is part of sample space. That's what we are trying to talk about. Okay, so if the outcome of an experiment is an element of A, we say that event A has occurred. So if the outcome of an experiment, if the outcome of an experiment is an element of this event A. So we say that A has occurred. So let's quickly look at the axioms of probability. Axioms of probability. We are trying to define to know what is expected to know under we are expected to know under probability. So let's look at the axioms of probability. So we are actually doing a lot of theoretical approach to probability today. Then we continue from there some other time. So axioms of probability. The first axiom, this one says that for every event A in a class C, we know for every event A in a class C, we know that the probability of A is greater than or equal to 0. Okay? For every event A in a class C, the probability of that event is greater than or equal to 0. That is, probability cannot be negative. Probability can be 0 if what we have under consideration, if what you have is not actually, if what we have there will not happen, the probability is 0. And if what we have will actually happen, the probability is actually greater than 0. So we should know that. Then the second axiom is that for the same or certain event X in a class, for the same or certain event S in a class, the probability of X is equal to 1. So let's take note of that. We should take note of that the probability of S is actually equal to 1. And that's actually represent the second axiom. Then the third axiom is that for any number of mutually exclusive events, what are mutually exclusive events? Two events are said to be mutually exclusive if they cannot happen together. So when we say we have mutually exclusive events, we can have mutually exclusive and we can have mutually inclusive events. So when do we say that two or more events are mutually exclusive? Two events are said to be mutually exclusive if they cannot happen together. So under this third axiom now, what we're trying to say is that for any number of mutually exclusive events, let's say these events are A1, A2, ... up to AN. Okay, let's say these are the events. In case of mutually exclusive events in the class C, let's say in the class C. So we know that P, probability of A1 union A2 union ... up to union AN, can actually give us the probability of A1 plus the probability of A2 plus the probability of ... P over AN. That's what we are trying to say. That in a situation whereby we have mutually exclusive events that cannot happen together, then this is how we write the probability. So in particular, if we now have two, we have all these events. If you say they are mutually exclusive, that's what we are going to have. But let's say we have just two events, A1 and A2. That is, if you try to narrow it down to probability of A1 union A2, let's say we have just two events. A1 union A2 simply means we are going to have the probability of A1, the first one, plus the probability of A2, the second one. That is what we are going to have. So we have some theorems on probability. But for the sake of time, we can actually check those ones out in the standard textbook. Theorems on probability. But I will only talk about one or two. Of course, part of the theorem is that we know that 0 is less than or equal to probability of A less than or equal to 1. That is, probabilities for every event A, the probability lies on this. That is, a probability is between 0 and 1 for every event A. Then we also know that the probability of empty. So if we have an empty event, that is, the impossible event has 0 probability. Is 0. The probability that when we are sure that that event is impossible, then the probability is 0. So then if you have event A and we have the complement of that event, let's say we have event A and complement of that event, the probability of the complement of that event will be 1 minus probability of A. That is, the probability that event will happen plus the probability that event will not happen is equal to 1, total probability. So if complement is You know the meaning of complementary set. So the probability of A complement now will now be 1 minus probability of that event. And of course, we've talked about mutually exclusive events. Then if A and B are two events, then probability of A union B will be probability of A plus probability of B minus probability of A intersection B. So that's what we're going to have. That's what we're going to have. So, and we have been talking about events. So under the mutually exclusive and mutually non-exclusive events, there are two events. The events can be mutually exclusive or non-mutually exclusive events. So under mutually exclusive events, we know that there are events which cannot happen together. There are events that cannot happen together. Let's just talk about the two types of events. We have mutually exclusive events. So these are events that cannot happen together. This is what type of events that we talk about. So for instance, in rolling a die, the event of throwing a 6 and that of throwing a 5 cannot occur at the same time. That is, if you have just one die, not two dice, so one, there are 6 faces in a die. So the event of having a 6 that will come up, and let's say 3 that will come up at the same time, it's not possible. There are two different. The event can only happen at different interval. So if you toss a die now, say you toss a die, one die, not dice, you cannot get 3. 3 cannot come up and 6 come up at the same time. So these are mutually exclusive events that cannot occur together. But we also have mutually inclusive. We have mutually inclusive or non-exclusive events. We have mutually inclusive, or you say mutually non-exclusive events. So in this case now, there are events that occur simultaneously, something that can actually happen together. Under mutually exclusive events that cannot happen together. Under mutually inclusive events or mutually non-exclusive events, there are events that can actually happen together. For instance, in rolling a die, the event of obtaining a multiple of 3 and the event of obtaining a multiple of 2 can occur together if a 6 is thrown. That is, if I want to toss a die now, the event of getting multiple of 2 and multiple of 3 by one toss is possible. So if I toss a die and 6 comes up, of course, 2 and 3 can actually divide 6. They are multiple of 6. So that one is possible under mutually inclusive events. Then there are some laws that we are going to talk about in probability. So we have the addition law. We have the addition law and the multiplication law. We have the addition laws. We have the addition law. Under the addition law, we only consider 2. Under the addition law, we consider 2. The first one under the addition law is that when we have for mutually exclusive events, say A and B. So under the addition law, if we have mutually exclusive events, say A and B, under the addition law, if you have mutually exclusive events, it simply means that the probability of A or B, we actually the probability of A plus probability of B. That's what we are going to get. Under the addition law, there are 2 that we consider: mutually exclusive events and mutually inclusive events or mutually non-exclusive events. But under the second one, mutually inclusive events or mutually non-exclusive events, if the 2 events A and B are mutually exclusive, it simply means the probability of A or B will be this. But when they are non-exclusive, mutually non-exclusive events or mutually inclusive events, what will happen to the 2 events? 2 events A and B, probability of A or B will now be probability of A plus probability of B minus probability of A intersection B. Under mutually exclusive events, A intersection B is not possible because the 2 events cannot happen together. But under mutually inclusive events or mutually non-exclusive events, A intersection B is possible. The 2 events can actually take place. But we are sure that under mutually exclusive events, that can never take place. That can never take place. We are sure. So we don't waste our time. We don't bother ourselves with that. So I'm going to take one example under this. I will take one example under this. Then probably we close for today. We're going to consider independent and independent events in some other class. So let's take one example. I'm going to take just one example under this. We are just introducing probability. So we are going to continue from there in our next class. So let's take one example. Let's take one example. Example one. Example one. We have a single card. A single card is drawn. A single card is drawn from a pack of 52 playing cards. A pack of 52 playing cards. So A, if event A is equal to drawing an ace, and event B is equal to drawing a 7. For people that play cards, you are familiar with all this. Then find the probability of drawing either an ace or a 7. Okay. Then B, the second part of the question, if event A is equal to drawing a king and event B is equal to drawing a red card, then find the probability of drawing a king or a red card. So this is the question. So we are going to solve this question. Then we close the class for today. So in this case now, we have a single card is drawn from a pack of 52 cards. Of course, people that are used to this, they know that there are 52 playing cards. So the first part of the question says that if event A simply means drawing an axe and event B simply means drawing a 7, then find the probability of drawing either an axe or a 7. That's the first part of the question. Then the B part of the question now says that if event A simply means drawing a king and event B simply means drawing a red king, it's possible to have a red king, a king that is red. So then the question now says, then find the probability of drawing a king or a red card. So now let's just solve this. We've gotten the question, so let's solve this, then we close. I'm going to stop the class. So solution. So extra information is actually needed to be able to solve this question. We consider the first one. So in a card, we have 4 aces in a card. In the pack of a card. So the probability of getting an ace now will be 4 all over 52. The total number of cards is 52. How many aces do we have in a card? 4. It will be 4 over 52. So that is the first one. Then we also have 4 sevens 4 sevens in the pack of a card. So let's say probability B now. A is ace, B is probability of 7. Will also be 4 over 52. That's what we are going to get. So the first part now said we find the probability of getting an ace or a 7 in the pack. So the probability of getting A or B, ace or 7, will now be the probability of A plus the probability of B. Because it's that you have ace or 7. It's not possible to have ace that is 7. Here will be 4 over 52 plus 4 over 52. Then we are going to have 8 all over 52. Of course, 4 can divide 8. That's 2. 4 here, 13. So the probability is actually 13. 2 all over 13. That is what we are going to get. So in this case now, they are mutually exclusive events. Events that cannot happen together. It's not possible to have an ace that is also 7. But let's see the second question now. We can have a king that is red. We can have king that will be black. So that one is mutually inclusive or non-exclusive events. So this is the A part of the question. So we go to the B part of the question, where we are asked to find the probability that if the card is a king and is red. The B part of the question. So what do we have? So in this case now, these are non-exclusive events, since we could draw the king of hearts or the king of diamond. So the king of hearts, there are 4 kings in the pack. Then 26 red. In the pack of in that pack of the card, there are 52 cards. 26 are red, while 26 are black. So we can have a king that is red. So the B part of the question now, we say 4 kings. We have 4 kings in the pack. Okay. Therefore, the probability of A will be 4 all over 52. Okay. Then we have 26 reds. There are 26 red cards. 26 red in the pack. The pack out of 52, 26 are red, while 26 are black. So if that is the case, then to have a red card, the probability of B will now be 26 all over 52. That's what we are going to have. Okay. So 2 kings, so we can have 2 reds. In this case now, out of the 26, we can have 2. We can have 2 red kings. That is, out of the 4 kings that we have in the pack of the card, 2 are red, 2 are black. So it is possible to have a pack it's possible to have a card that will be red and it will also be king. That's what we are trying to say. So if that is the case here, we have 2 red kings card in the pack, and that will be probability of, that will be A intersection B. That is, A is probability of king, of picking a king. B is probability of picking a red card. So it's possible to have a king, a card that is a king and it's also a red. So the probability A intersection B, which actually stands for the 2, will be 2 over 52, because there are 2 red king. There are 2 red cards that are also king in the pack. So this one, there is possibility under mutually non-exclusive events. So the probability of getting a card A or B now will now be probability of A plus probability of B minus probability of A intersection B. So the probability of A is 4 over 52 plus probability of B is 26 over 52 minus probability of A intersection B will be 2 all over 52. So what do we get there? Of course, we can take the LCM, it will be 52. We have 4 plus 26 minus 2, and that will be 28 all over 52. Can 4 divide everything? Yes. We're going to have 7 all over 13 as the final answer. So I would love to stop here because of our time. We are going to continue from there. We are going to continue from there in our next class. We are just trying. I've just tried to introduce probability. So we actually stopped at event and non-inclusive and non-exclusive and non-inclusive events. So under addition law. So we are going to continue from there in our next class. So we are going to continue from independent and dependent events. Thank you, and God bless you all.
Mathematics made easy. easy, no more fear. Target online class, we got you. Wherever you want it from, we got what you need. Target online.